Denodo is a leader in data integration and data management. We use a modern approach called data virtualization, which is a real-time data integration and data delivery approach. Global companies across the world have successfully used data virtualization for projects such as Agile BI, cloud data integration, data lakes, and also data services, and you can benefit too.
Welcome everyone for the last day of the MIT CDOIQ of this year. My name is Jean-Pascal Chauvet. I'm a strategic consultant at Ab Initio Software, and I'm the track producer of track 6. Now, a bit of housekeeping. I think by now everybody knows these sessions are being recorded and will be available in a couple of months to everyone. We are going to have a Q&A at the end of the session, so feel free to ask your question on the Whova platform. Now, today's topic, it's what CDOs should know about quantum computing. I'm very excited about this session, which is going to be in 2 parts. There will be one part for the next 1 hour, then we are going to take a little break, and then a second part after the little break. So please be sure to come back for the second part as well. This will be a panel discussion with Dr. Robert Sutor, VP of Corporate Development at Quanta and former IBM tech executive. Also with Dr. Naguib Attia, former Distinguished Engineer and VP of IBM Global University. Also with Dr. James Meng, Senior Scientist at the Supercomputer Center at the University of California in San Diego. And with Dr. Michael Haydock, IBM Fellow, VP and Chief Scientist, Data and Technology Transformation, IBM Consulting. A warm welcome to you, gentlemen, and over to you.
Thank you very much. Let me bring up my screen here. So as this sets up, may I just verify that you can see my screen?
Yes.
Okay, very good. This is a very brief introduction to quantum computing, and in these few minutes this morning, I want to separate out what I'll call the hope from the hype a little bit, to give you an idea of what quantum computing is. Why are people interested in quantum computing? And really, what will it take to get there? Now, what do you do along the way? What do we really do when we get there? What sorts of problems are we trying to solve? Well, we'll certainly go into much more detail in that over the rest of the couple of hours of the 2 parts here. So let's jump in here. Okay. So first of all, we have to distinguish what we're calling quantum computers from classical computers. Now, classical computers are really what goes back to the 1940s, the 1950s. If you remember, as I show in the upper left-hand corner here, the UNIVACs. These are the systems that really all come down to a lot of zeros and ones, and interesting things you can do with them, both computation and storage as well. But as we know, this original idea of having a few very large computers over the decades has gotten us to the point of having, as Carl Sagan used to say, billions and billions of processors of different forms here. And this could be the laptop you have, it could be your smartphone. On the lower right, I include a photo of a car that was showing the different processors in the car, and you can see where these computer processors can show up. This photo is more than 10 years old. So this, if you will, the revolution of driving classical computing into just the way we drive is in fact far, far more advanced now than it is. On the lower left is the latest state of the art of the supercomputers. It's been built at Oak Ridge. Now, if you follow supercomputers, they leapfrog each other on a very regular basis. I was with IBM until the end of February, and we very proudly would show the Summit supercomputer, which the statistics, the specifications on that were just amazingly fantastic in terms of the number of processors and the amount of storage and so forth. This system, the current winner, is 10 times more powerful. So you can see that classical computing is continues to get better and better, though we're no longer tracking to Moore's law, which was postulated around 1964, which said that every 18 to 24 months, our computer systems would get twice as powerful, twice as small, and use half as much energy. We really haven't been tracking to that for quite a long time. But there are always going to be clever ways of improving some of the capacity of these systems. But there's only so much we can do. So even if we might have these petabytes and exaflops, right? That's a lot of floating point operations and the cloud, and everything that entails, and the billions of CPUs, from small devices to thermostats, all the way on up to these supercomputers. There's some hard problems that are still intractable. Now, this is a great word to think about the evolution of computing, being intractable. It doesn't mean that things are impossible. It just means that with what we know how to do today, we can't solve them in a satisfactory way. And satisfactory might mean, well, we can solve the problems accurately enough, or we can solve them in a short enough period of time, or using few enough resources, or less energy, or just less money, right, to do these types of things. And so because of this, and because this involves some very important problems, we continue to search not just on the classical side, but also for alternative ways. So let me just, okay. All right, on the right-hand side here, these are some of these example hard problems. It turns out, the very top one here, that the simulation of physical systems, and by physical systems, I mean you. I mean every chemical reaction inside your body. I mean every atomic molecular reaction around you, what happens in stars, everything that way, pharmaceuticals and so forth like this. These sorts of problems are notoriously difficult to simulate, to calculate using classical systems. And really there's no reason why any particular problem should fall easily to a classical approach, because the classical approach, while universal in a sense, has no real guarantees of any particular problem being easy to do, or being easy to do in a short period of time. Now, as we think of these physical systems, and it's often easy to think of chemistry as these, well, the development of new batteries, right? Lithium sulfide batteries. We've all seen the changes that having lithium batteries show up in so many different places, not just in vehicles, right, for transportation, but ultimately for materials, and honestly, in a long time in medicines. What we're doing now with quantum computers, just to tell you this right up front, they're going to have to be extremely large to deal with pharmaceutical applications here. Creating fertilizers, extremely expensive energy-wise. Can we do a better job there? Then there are certain types of optimization problems, certain types of simulation problems, I would say. And these could be, if you're familiar with Monte Carlo examples for simulation. Not every optimization problem. We have an incredible toolbox for doing many of these sorts of things. But once again, to really optimize, we continue to develop new techniques. We continue to develop new ways of linking hardware together, HPC, to do a better job there. Machine learning, of course, AI is becoming pervasive. Anything we can do there is better. Part of the reason why this is important. It is the mathematics that underlies it. Well, it turns out that a lot of that same mathematics is useful in other fields, computational fluid dynamics, right? How well a liquid or an air flows through a pipe, over a wing, over a car, any of these sorts of things. Weather forecasting. Now here we're getting, honestly, into really difficult and problems that people say, oh, wouldn't it be great if we could do this perfectly? It's extremely difficult. There's a lot of data. There are a lot of differential equations and so forth involved with this. But nevertheless, it's a problem that people continue to attack. And then optimized energy networks, right? There's the energy distribution, but think of all the places we are now creating energy. And where do they flow? How do they flow? And the general idea of optimizing networks in different ways are very hard problems and would have big payoffs here. Now, these problems, when we think about them, and I'm using the phrase galactic scale problems, the reason why I'm using this hyperbolic term, if you will, about galaxies, is that literally for some of these problems, when you do the calculations, when you need to represent the information, it's an astounding amount. So, for example, one case I've used for a little while is to just talk about a caffeine molecule. So I'm sitting here in Boulder, Colorado. It's the morning. I have not had my coffee yet. Looking forward to it a little bit later. But if I think of the caffeine that's in that, and I zoom in and I think of just one caffeine molecule there, the amount of information, right, that would be used to represent that caffeine molecule in a working way inside a computer, right? And now let's translate and think of that information as zeros and ones, the number of zeros and ones we would need. That number is approximately 10% of all the atoms in the Earth. And so think of the Earth, think of all the atoms that compose everything, take 10% of those, count them, and that's how many zeros and ones we need just to perfectly and accurately represent caffeine. And honestly, we're interested in other things other than caffeine, much bigger, much more interesting. And so this is why, as we start thinking of larger problems, yeah, we get beyond the Earth, we get beyond the solar system, and we do seriously start talking about galaxy-size amounts of either the storage we would need or just the time it would take to do anything with this. Classical computing is wonderful and, as I said, universal, but knowing that there is a classical solution doesn't help if it takes 3 million years to actually do the computation, right? And so that's why we're concerned here. So what can we do? Well, here are the two supercomputers, Summit from 3 years ago, the new one here. The first thing we can do, and what we frequently do, is we just approximate. We try to do the best we can in a limited amount of time or with a limited number of resources or for a limited amount of money we're willing to spend and get the best answer we can under those constraints. And maybe that works, but it doesn't always work. So that's why I gave you the list of the hard problems. Well, we can keep building larger and larger supercomputers, and the work on new algorithms doesn't stop. And hope that these new algorithms, these new approaches, especially hybrid approaches, allow us to get better and better and better. But nevertheless, we get this sense that we're running out of steam. Right, that we're making a little headway on the very hard problems, but not enough, and certainly not enough to build these types of supercomputers to tackle them that take up an entire extremely large room, or as they say, football fields worth, and so forth, and things like this. Well, the other approach is to look for an entirely different type of computing. Right, that is not focused on the zeros and ones that have served us so well for over 70 years, and by the way, will continue to serve us forever. I mean, classical computing has a lot of advantages, a lot of applications. Classical computing is not going away by any means, right? But are there completely different approaches that maybe extend some of the basic ideas like bits? so that this new model with the algorithms that are associated with them could tackle some problems, not every hard problem, but some problems in a completely different way. And those problems may be relatively easy for this different approach. And I don't like to use the word hybrid as we move forward and we think of the new types of computers with classical computers. It's an integration. I mean, this is what computing is. We learn new things, we develop new techniques, we create new hardware, and we blend it in what we do before. So you wouldn't call your laptop, for example, a hybrid computer because it has a GPU in it, right, to drive graphics. No, it's just integrated. It's just part of what you do. And in the same way, this integration is going to be important for these new types of computers because we want to use the classical hardware, the classical algorithms, the other software for what they do best, and the new types are what they do best. And in fact, one of the features of classical computing is the control structures of how you make decisions of what to do under what circumstances. That's logic. It's not so much classical computing, it's basic logic. So you use logic and then you tie that in with these new things today. And so the idea is to help make some of those problems that I showed more tractable. Right. So it doesn't mean we can completely solve them. We hope to do very well on some of them. But even if some of the applications of those problems I showed you remain out of reach in their largest scale, it could pull things in that we can tackle problems significantly larger than we could do before, if not entirely solve the problem completely. And this is where quantum computing comes along and the quest for what I'll call practical quantum advantage. And so practical quantum advantage here is the point where the combination, the integration of quantum computers with classical computers to make new types of systems can do things. Here I usually insert the word significantly better than classical systems can do alone. Honestly, I don't think it's worth it if it's just slightly better, right? This combination and all the work we're doing on it has to really show a significant improvement over what we can do. Now, sure, the first examples will be slightly better, but the goal is to be able to jump much faster and further, and not in just a linear way, not just to do things twice as well. For example, what's left of Moore's law will catch up and you can do things twice as well. There are other ways of measuring the complexity or the hardness of the problems. And it's this use of quantum that really has to push us into those much more significant improvements, particularly as the size of the problems get larger here. Now, the motivation for quantum is, if you look around at alternatives for the computers, your smartphone, your laptop, whatever, is that we could say that nature is the biggest computer, right? It's unique and is the biggest computer. And here, all of the data are all the quantum particles, for example. And here we're thinking of nature in a very particular way. We're thinking of the very small. We're not thinking, frankly, about gravity and so forth like this. We're talking about quantum mechanics, which is the model in physics which describes the behavior of things at the very smallest level, photons, electrons, and so forth, and things like this. And so this is the data, right? And there are uncountably many of those. And the apps are how all these particles come together and interact to do useful things like create you and me and everything around us, right? So we have a clear sense of the data and we have a sense of how it works together. And if we think of the universe as something we're trying to implement on a computer, frankly, nature does a pretty good job. So can we take that? Can we take the basis of quantum mechanics? And admittedly, it's extremely strange the way quantum mechanics works, but can we use the parts of it, things like superposition and entanglement and interference as the model for a new way of doing computing? And that is what we call quantum computing here. And so we build a programming model around these, and then we have to build hardware that supports it. Now, on one hand, you could manufacture these core quantum particles. And this has been a reasonably successful approach, although the computers are still small, or what are called superconducting quantum computers. And so here you create a chip. It's a combination of semiconductors and some analog computing, and you chill it down close to absolute zero. And oftentimes when we talk about this, we do talk about coldness and close to absolute zero, because that's when things slow down. That's when we can start controlling all of these quantum effects, and we can make these computers at these very cold temperature do the things we want to do, as opposed to have all the quantum noise around us somehow interfering with this. So I show you above here a cold atom approach to this, where we're using atoms. In fact, to implement qubits, which are the basic computational units here, those are held inside a glass vacuum tube. The tube on the right-hand side is about 2.5 inches tall. It's very small. And we've demonstrated that we can use over 1,000 of these atoms as quantum bits or qubits here. On the lower right is just an example of it's a somewhat arbitrary circuit. It's a quantum circuit that does do interesting, if you will, quantum operations to qubits here. So how do you build these things, right? And here, I want to get serious about this, because it is non-trivial. And sometimes in what you read about, you hear, oh, somebody has this great success. Well, or builds this computer, or isn't this amazing? Let's get real for a moment. 20 qubits, right? These computational bits, it's not going to save the world, is not going to solve the biggest problems. You can simulate 20 qubits on your smartphone, frankly. So while there are many technologies, and these qubits, the core of the computational the units, if you will, here, we're going to need many of these. And so when we hear about these single digits, double digits, and even triple digits, it's like, thank you, very nice progress, but we have a very, very long way to go. Quantum computing is not additive. You don't have a 100-qubit quantum computer and build another one and then get a 200-qubit quantum computer. We have to have ways of connecting these systems together in a quantum way in order to scale this way. So we decide on a certain type of quantum bit technology, and it could be cold atoms, could be superconducting ions, though I don't believe ions will scale very well, photonic approaches and things like this. You arrange them in some way, you trap them in some way. So this is the 1225 array of cesium atoms that we have built in a lab. These could potentially be used as computational units, quantum bits, qubits in a computer. Now, once you have them there, you actually have to control them. You put them into a superposition, which is, if you're familiar with the mathematics, it's essentially just a linear combination of these in certain ways while you're obeying the laws of quantum mechanics. You have to, at various times, entangle qubits together to perform some operations. And then algorithmically, you use techniques like interference to consider many possible solutions, but your algorithms are systematically reducing the number of possibilities of what is likely a good answer. Now, probability is involved here typically, and so you may need to run the calculations a few times. So really, to do all this, and if you think of the math, it's linear algebra, it's complex numbers, it's probability, and things like this. And then you repeat this as necessary here. So it's not meant to replace classical computing, as I said before, right? Quantum computing is universal, but you would not use it to do the simple things like you do in a classical computer. You would have a very large, very slow, very expensive computer. You want to use classical means to do the classical algorithms, right? So we do believe we can enhance machine learning in a significant way, perform operations and simulations. People usually mention financial services first. We by no means believe it's going to be limited to that industry alone. They just tend to be at the forefront of implementing any sort of optimization, simulation of approaches to these things, and then help in areas like computational chemistry. And that is why, of course, when I gave you these example hard problems, these are the categories that I was talking about. And all of these hard problems people are now starting to attack with quantum computing. Now, when I say attack, I do not mean completely solve. There is no quantum computer being used anywhere in the world in production today. The systems are too small, but we have to learn how to do this. This is new ground, right? How do we use these algorithms? How do we combine classical and quantum approaches? How do we get closer and closer and closer to these, all the while improving the underlying quantum technology and on our way to things like fault tolerance and error correction as well. So to conclude here, just to give you an idea of what we expect, and here, along with the rest of what I've said here, is I want to give you a framework for thinking about this, about thinking about quantum computing when you hear about it in our remaining parts of these sessions, but also moving on here you know, we don't just wave our hands and say, oh, it's going to be great. Right? Well, when we think of these quantum bits, these qubits, and I have not defined them here, but the definitions are easy to find. We're going to require tens of thousands to millions of quantum bits. So get excited about progress, but no one, as I said before, is going to solve any significant problem with a few dozen qubits, right? It's just not going to happen. Progress is good. The qubits must all function, all right? I always thought this was a given, that if you were making a quantum computer and you were talking about the number of qubits in your system, that they all worked. Not everybody seemed to believe that was the case. So I'm going to say, let's assume they all work, okay? And they all need to function with very low error rates, right? Ultimately, error correction, fault tolerance will sweep that up, but we have to be able to control the errors and the effect of noise in the systems. Now, because we are creating these as physical systems, right, they tend to hold their values, but then become chaotic over time, right? It's called decoherence. They need to maintain their values sufficiently long for us to do interesting things with that information. And these are the 1 and 2 qubit operations. They have to be fast enough relative to our decoherence time. And once again, low error rates. They must be richly interconnected. If I give you 1 million qubits and they're completely disconnected from each other, that's next to useless, all right? It's the connectivity that gives you entanglement, and they must be entangled in enough ways. Enough qubits must be connected in different ways to other qubits to make the algorithms work efficiently, all right? And this all goes down to, ultimately, when you get through this, when you get through your calculation, you have to read out the results in an accurate way. Now, every time we talk about technology, whether it's cold atoms or ions or superconducting or photonic or diamonds or things like this, every single different approach to quantum computing has different challenges and sometimes advantages to do all of these things. All right. So demand answers for all of these when you talk to people, because it tends to be that if of these, and I've listed 6 of them, people tell you the 2 they really like, or the 2 they look really good on, right? And then maybe don't mention all the others. But it's going to be the balance of getting all of these things and getting everything, you know, more of them and better over time, that will eventually get to our target. So I'm going to stop there, and the rest of this will be much more about actually doing something with quantum computing and getting ready to do something with quantum computing as well. So thank you very much. And Naguib, I'll turn it over to you.
Thank you, Bob. Thank you. What a wonderful starting point. So I'm going to take this discussion through a different angle. Bob presented the technology and the challenges of technology. I think we also need to be aware of the challenges of the human and the skills needed. So we don't just produce a technology and look back again to what happened to us on the 60s and 70s when we were doing computational and all of that. And finally, we realized we need the computer science department in the mid 70s. And the academia was about 10 to 15 years behind industry. So this is a part we'll go and take you through. Are we also ready for quantum computing? So when I look at this one and I say it was presented in 2019, but still fact today, are we investing enough in quantum computing? Are countries as well as universities, as well as industries, investing enough to come to the problem and solution, solving the issues that Bob just mentioned? My research found that we're not yet there. If you look around, companies and countries are still debating how much should we invest, how much should we think about computing and quantum computing investment, as well as the rest of the academia challenges. So next slide, please. So I did a little bit of study searching about where the status today, state of the art of education on quantum computing. And to my surprise, I found that most of the people offering quantum courses and quantum introductory and quantum computation are all coming from what you can call them small online course providers. Very few, if you look at the next list, please, very few universities. And I know I used to run the program inside IBM Skills Academy. We offer an introduction to quantum computing. I can tell you, and all of you will realize that none of these courses will produce enough knowledge or enough skills for someone to work on the quantum computing challenges and quantum computing industry as we think it is. So I did an analysis of most of these courses, and we're more than welcome all of you to go and visit these websites. That this is just like someone telling you a story about the quantum computing. This is not someone that will really get you into the quantum computing knowledge and foundation and the science of it. So I did another search and I found, next please, that some universities are offering quantum computing, I call it education. I'm not going to say anything about education. And then suddenly I found that all of these programs are either a master or PhD. Next slide, please. So if we are going to focus on masters and PhD and we ignore the foundation, which is the undergraduate, I don't see it yet an undergraduate, call it a major or a minor, that focusing on quantum computing and quantum computing technologies and all the area that just Bob mentioned doesn't exist yet. So if it doesn't exist, we are going to be faced with the same problem that we had before. We will have few PhDs and we will have very good few top-notch researchers, but we will not have the manpower behind them that they can go and work in the financial sector, in the pharmaceutical sector, in the other industries that Bob mentioned. So you will not have enough manpower if you assume tomorrow that the problems Bob mentioned are solved. We've already had the quantum computers, and we now need people who write software codes for quantum computing. We need people, researchers on the hardware of quantum computer, and we need to implement those techniques and put the material and put the computer, if we already have it, at a financial institution or others. We will have no technical, no people, no resources that can be the mass workers that we will need. So next slide, please. I found that this is what is happening. There's not enough quantum programs worldwide. Most of the universities that and the list I gave you, they're all focused, maybe centralized in US and some European countries. One in Japan, one here, one there. That is not enough. If we want to do a quantum computing revolution, and if we want to bring the quantum computer to the forefront, we have to look at that the quantum knowledge is also worldwide and is also available to the rest of the world. Few quantum software developer classes. You cannot just think of the hardware side and work on the physics and work on the manufacturing of a quantum computer without thinking of the software developers that need it for that. No courses yet is tackling this at any university. Do we have enough graduates in the next 3 years? I'm just saying, assume the first computer is going to be implemented at one of the financial institutions at one place. Do we have any graduate that can be higher than these, which I just mentioned before? No programs yet can give you a graduate that can say, I have a minor in quantum computer. So now we're facing two big issues. The first issue is that the quantum computer need a lot of talent and a lot of background for masters and PhDs as well as undergraduate, but the world did not put a plan yet in place. And I can see some countries announcing some initiatives here and there, but there is no action yet. No one started to say, okay, now we're going to have a strategy for quantum computing. We're not going to go back to what happened to the world in the 60s. Academia needs to be in forefront, not to wait 10, 15 years to come back after the industry to say, oh, wow, there is something called quantum. Let's now create either a quantum school or bundle quantum under the AE major or under computer science major, as we used to do. And we did the computer science was bundled under physics department or math department. We need to start now thinking, we need to start now preparing from country level to university level to industry level. Next slide, please. And with that, I thank you all for listening. The rest of the hour is going to be a panel between the four of us here. And I'm going to challenge Bob as well as Michael, as well as Jim, with some questions about, with all these problems we just put on the table today. We put the issues from an industry point of view to the skills and academia point of view, and now we would like to brainstorm among ourselves. So the first question I'm going to ask you, Jim. Jim, you've been working very long years with me and with IBM implementing the quantum computing from a skills academy. And you try to take this across the US and global initiatives. What do you think that is missing on the training and the curriculum around quantum computing?
Right. Good morning, both Bob and Naguib. You really have done a superb job. To answer your question, 3 years ago, I tried to start here at Supercomputer Center at the UCSD, and I searched around. UCSD did not really have any quantum computing educational programs. And I worked with the physics department and chemistry, mathematics, computer science. And the issue came out really, it appears that a very large barrier to quantum computing education is that people have a very deep mystique about quantum computing, that you got to have a PhD in mathematics from Princeton to do anything about quantum computing, or that you have to be really, like those highly trained computing, deep in math. And that, to me, that has been the largest barrier to overcome. So the quantum computing educational programs really has to find a way to overcome that issue. So, and actually, Naguib, given your experience advocating, implementing the IBM Global University programs, what are the approaches or incentives that the IBM Global Universities have tried with your alliances of universities?
So when we looked at quantum computing as well as the rest of the latest technologies that you already know, like AI, data science, security of cloud, the first challenge was, do we have enough, and I'm now talking globally, I'm not talking about the Ivy Leagues universities, do we have enough faculty aware, trained, well-positioned to tackle these new advanced technologies? And so the first thing we did was look at how can we train faculty to become at least a coach, or at least creating a curriculum by themselves. And if they need to create a curriculum by themselves, we needed to support them with technology. So we supported them with another program that was about we call it at that time, academic initiatives, which is all the resources of technology were available for free for teaching and research. And the third part of the equation, now you provide me with some coaching, you provide me with the technology, can you provide me also with some cloud access and cloud utilization? So we offer some limited, you can't open the cloud for free for all faculty worldwide, and I think with that, we helped many universities to start jumping into, so the quantum courses, introductions, quantum tools to use. So we're available to academia.
Right. In UCSD here, we do use IBM QISKIT, QISKIT. It's a complete end-to-end suite of instruction as well as simple quantum algorithm programs, Python programs from end to end that students can use in the practice. To me, that it's a real fundamental contribution that IBM has made. I searched the other companies like Google, Microsoft, D-Waves. They really do not have that focus or end-to-end kind of infrastructure to help promote the quantum computing. So I have to say IBM has done a tremendous job, especially all of you are from IBM. You're all IBMers.
We're alums. I would also emphasize, actually, Qiskit is open source. And like many of these new technologies, the way for them really to get a foothold is to use the community to build a very strong foundation for software development. And that's what Qiskit is. When we started looking at that and thinking about the languages, we chose Python because, well, gee, there are 8 million Python developers, or at least there was at the time. So that was a way we thought, particularly for the education market, because they usually teach Python for computer science now, right? It was a way of quickly going. I also wrote a book, in fact, doing that connection, because I think the future is computing. It's not classical, it's not quantum. And so going back to your point, Naguib, about how we teach this has to strongly become part of the computer science departments, not just be part of physics departments.
Right. Thank you.
I also wanted to add to Bob's point that the time when you made a decision to use Python as the basic language to run a quantum computing, that was a very wise decision, because in my mind, that the next largest impact the quantum computing is going to make is in the AI and the machine learning.
Mhm.
And the machine learning, all that is in Python. So this provides a seamless bridge over, and that's going to facilitate the wider applications. I also, I was listening to your earlier presentation about this is not a hybrid computer. This is another way of creating that central processing unit. So in my mind, I believe that in 10, 20 years, our iPhone may have a little interface with quantum computing output. Your iPhone don't need to do the computing, but you should be able to receive the quantum computing output. And that will push everything toward real time. And that's one of the largest challenges for chief data officers, is that by the time you guys give me the decision, that's 1 week late. And it doesn't really help that much. But if the most intensive, computational intensive part are dealt with in a very short time and delivered to the classical computer interface and deliver the results. So all of a sudden, many of the decision aids that the chief data officers were dreaming about will really becoming true. And that, to me, is the bridge between the CDOs and the quantum computing.
Thank you, Jim. That leads me exactly to the question that Bob will be the one to answer here, Bob. Bob, okay. What would the quantum computer at the edge do? Because just as Jim mentioned, compute quantum will be on the Apple. And what are the potential applications?
Well, for me, on one hand, this links back to this machine learning question. In fact, quantum machine learning is a thing. It's QML. And you get two buzzwords at the same time. If you do quantum machine learning on the cloud, you get three. Okay, so but the idea is that really, where will techniques of quantum computing augment machine learning? And I'm going to leave it as homework, really, to the attendees here, of where the different places, and there are 3 or 4 of them, where we do think quantum will improve the ways we do machine learning today. Now, there's a little gotcha, and the gotcha is that quantum computers are not big data machines. So if you ever read about somebody pumping terabytes of information through a quantum computer, just stop reading it right there, because they don't know what they're talking about. That will come in time. Now, if we look, though, at some of the really interesting things that are happening in AI and machine learning, one of them is federated learning. And so federated learning, where not everything is done in one place, not everything is done in the center of the cloud, but some of the training and the use of the machine learning is done at the edge. And the edge can be lots of different places, and there are different definitions, so I'll be a little vague here. Whether it's a cell phone tower or your actual cell phone. Certainly, if you look at military applications, the edge can be a plane, it can be a ship, it can do different things like this. I think it's very short-sighted to only think of quantum computers as being supercomputers and data centers. Every single time in the history of computing where we have thought, here's something we'll do in one big room, probably air-conditioned, right? And we'll have a few of them, and they'll tackle hard problems. We then turn around 5 or 10 years later and discover there are tens of thousands of much smaller systems. So as long as this quantum, I'm not going to call it a revolution, but the evolution of quantum and this new integrated way of doing computing is going to take a while, we should think about this. So how will quantum play at the edge? For this group, how will it play with machine learning? But I also want to turn this around completely. And I think this is really in line with this conference is certain people, and I'll admit people like me, start by thinking of processing. And very smart people after a few years and say, stop talking about the processing, talk about the data. Bring the processing to the data. Worry about the data. It's all about the data, right? Yeah, we'll figure out how to do the computing around the data, but it's the data problem. It's not a processing problem here as well. Well, qubits encode data in quantum states. Quantum memory, once we develop it, will do the same. Quantum sensors like atomic clocks, accelerometers, radio frequency antennas will encode quantum data. This could be a huge amount of data that will be first created in quantum form. How are we going to process that? Not just going to all change it into zeros and ones and do things, right? So there are going to be very rich connections between quantum devices, quantum memory, quantum networking, and quantum computing. So for the people on this, follow the data, right? And that should be why you're interested in quantum.
Right. Thank you. Thank you. Well, that leads me to a question to Jim here. Jim, with your already some experience and some trials and errors at academia, what do you think the academia best approach to go after quantum? Technologically, educationally, training, it's upskilling, all the above.
Okay, that's a very big question. I think that if we start talking about quantum computing only after postgraduate, we lost already. I really believe that the high school curriculum should start dealing with quantum computing concepts, not so much get into the algorithm, but to understand, like Bob said, the nature is a big computer. And the data is in all the things that just keeping us alive, electrons and fluid exchange or whatever. And also we are the applications. And that is a very profound concept. And that concept requires no PhD in mathematics or physics. We all are manifestation of the quantum underlying quantum physics that's governing our entire existence. So to start out, I think in high school, the concept, the fact we are just a manifestation of the quantum phenomena, that should be instilled in students' mind. And therefore, when they do come to deal with quantum computing, they don't have this, oh man, that's hard. I mean, that ain't me. I don't want to deal with that. I mean, it just, right now, our biggest problem is 99% of the students are automatically off the chart. And unless we can deal with that as early as possible, we're not going to have success. And number two is when we do want to introduce quantum computing to them, and what they really only need is a linear algebra, the basic math. And I think that the freshmen, and they should be equipped with that. And once you have the linear algebra, you're no longer bogged down by kind of strange notation and all that. And then people can get the feel that the quantum computing are really manipulating those quantum and change their faces. And in the process, you enhance the capability to do the computation that a classical computer digits don't possess. And that kind of basic concept, once we make those points clear to them, they should be inspired. They should be inspired to learn more and wanted to know more. And that's where the programming can start. So, and start out with the programming will be very difficult because they know how to push buttons and all that, but it doesn't really lead to the real, intuitive kind of understanding. It's like almost like some cloud, mask over. So what is that? What does that do? But once you, and that to me too, it happened to me. I started looking at this 4 years ago after dealt with you, and I find it's fascinating. And the more I got into it, the more excited. And so, my course has been taught for 2 years now. I just finished the 2 years. Unfortunately, the attendance is very, very low. The issue is, do I have a graduate degree before I can come in? Imagine, no, you don't need that. And how do you, overcome that? And to me, I thought really needs to give them the basic intuitive understanding that nature is a large quantum computer.
Thank you, Jim. Thank you. Jane, we have about 4 minutes for a fast 1 or 2 questions from the audience, please.
So I have a question for you on the software side. So I'm a software guy, and when I develop applications in Java or Python or C++ or whatever, the fact that there are zeros and ones underneath, I don't really care. I don't really need to know how that works. So if we project ourselves 3 years in the future, 5 years in the future, can we make that same assumption about a quantum computer if indeed you guys are going towards implementing the programming layer, reusing what exists today, like Python?
We will blend them, and so you may not care about zeros and ones, and frankly, there are a lot of other things you don't care about.
That's right.
If you're programming to a smartphone and you say draw a red line on the screen, you don't care about the actual pixels. You just assume that something is going to do it. However, let's go back to really kind of basic things with programming. Let's suppose I do this. I'm going to say let x equals 10, and now let y equals x. You can't do that in quantum computing. You cannot copy data. You cannot extract things from databases without destroying the original copy. So while you may say, yeah, I'll just keep using this high-level things, when you do some of the fundamental programming in quantum computing, the model is radically different. So you expressed it in terms of, I don't care about zeros and ones, but you do care about the control structures. You care about the looping. You care about a lot of things that are inherent to the classical model that do not exist. Now, the goals for all of us are to build a good software stack. At the bottom, it's going to be very hardcore. It'll be close to the hardware, right? There will be experts who know how to do this. But at the top, you're going to say, here's a solution. Here's my data. I don't care how you're really doing it. Go off, solve the problem. So yes, we are creating with QuizKit and other things as well, a layered stack from the hardware, the control, to the optimization, all the way up to the applications. So that's coming along, and is an area of great research and indeed commercial interest as well.
Great.
Yeah, JP, along that line, the QuizKit, QuizKit, I hope everyone can take a look at that.
Okay.
You can really do what Bob said. You go in there, you look at one problem, and then you can experiment interacting with the program. You change the parameter, and then it gives you the visualization. It's really fantastic, and to me, that it's almost like a computer game. Okay. Except that in that interaction, it enhances your understanding of what does the quantum computing trying to do. And one of the most vivid demonstration is the quantum Fourier transform. Right. And they use the so-called block sphere visualization. It's really, really very intuitive.
Interesting. Okay, well, thank you for that. I think That's something definitely I'm going to look at, and the audience probably would be very interested as well. This is the end of part 1 of this session on quantum computing. So we will be back in half an hour with the same group for the part 2 on this discussion. So please come back in half an hour at 10 o'clock. Thank you.
Okay, thank you.